Hi, and welcome to week 2. So to start off with this week, we're going to be having a look at function composition and inverse functions. So just to remind ourselves, what is a function? We said that a function is something that consists of 3 things. It consists of a set of inputs, a set of outputs, and some rule which takes each input to exactly one output. So for example, we could have 1, 2, 3 as our input, which we also call the domain, and 5, 6, 7, which could be our range. And we could have a rule which says, okay, take 1 to 6, take 2 to 5, and take 3 to 7. That's a function. And then we also said it's totally fine to have situations where, for example, you take multiple inputs to the same output. So here we have a domain of 1, 2, 3, and a range that is just a smiley face, and a perfectly good function takes 1 and 2 and 3 to smiley face. So both of these are perfectly good functions, but if we had a situation where we had just 1 as our domain and 2, 3, 4 as our range, and we made the rule that said 1 can go to 1, 1 can go to 2 or 3 or 4, then that is not a function because it's violating the rule that says each input goes to exactly one output. Okay, so I'm sure you're familiar with this, but having these in mind is going to help for what we do next. So we've seen that functions are really, we can think of as a process which takes an input and does something to it and produces an output. So there's no reason why, if we have 2 functions, say an f of x and a g of t, and it turns out that the set of outputs from G is the same as the set of inputs from F, that we can't just kind of create this combined function which starts out taking an input, puts it into G, gets the output from G, and uses that as the input to F, and then finally gets the output from F. Let's draw a sketch of that. So the idea here is that we have 2 functions. We've got our function g, which has a certain domain and a range, and we've got an f that has a domain and range. And the key thing here is that the range of g and the domain of f have at least some things in their set that overlap. I'm just going to use the same for both, but it doesn't really matter. And now let's just think about G. Now G can have any old domain, so let's say 6, 7, and 8. And I'm going to say the range of F is going to be a star and a moon. Okay, with me so far? Now, let's finally assign our domain to our range in G. So this says that our G of 6 is equal to 1. This says that G of 7 is equal to 2. And this says G of 8 is equal to 3. And I'm going to decide that 1 gets assigned to moon, 2 gets assigned to moon, and 3 gets assigned to star. Okay, so I've just created 2 functions so far. But now I can create what's called a composite function, which really maps from the domain of G, from my 6, 7, 8, to the range of F, because it's a rule which says, okay, I'm going to take 6 to 1, but I know that 1 goes to star. So in fact, I'm sending 1 goes to moon. So I'm sending 6 to moon. So now I have a function which I'm going to call f composed of g, which sends 6, 2, star. So I can actually use equal sign there. And if I follow through with a different input from G, I can take 7 and that goes to 2. And if I follow through, that says 2 also goes to moon. So F composed of G of 7 is also equal to moon. And finally, if I look at 8, 8 goes to 3, 3 goes to star, so F composed of G goes of 8 is star. So the idea is really that I've just chained together two functions, and I could keep going with more chains, but usually we're going to stop there. So let's have a look at see how this works in kind of slightly more formal language. So suppose we've got a function y, and it's a function of x, and it's according to this process here. So y is equal to x squared minus 1. And in turn, we know that x is some function of t via the process x is equal to 3t minus 4. Is there some way that we can combine these so that we can actually say that y is a function of t? Well, yes we can, because we can say, well, look, we've got y is equal to x squared minus 1, but we know that this x is equal to 3t minus 4. So we might as well just say that y is equal to, well, x squared, so I'm going to have 3t minus 4, that's x, all squared, minus 1. And notice that we've changed this over, so now in our new formulation over here, y is a function of t, whereas over here, y was a function of x. Why might we want to do something crazy like this? Well, we'll get to that in a moment. I just want to get some notation going. So you'll see that I've already used a little bit of this notation, but our formal definition says that if we've got functions f and g such that g takes inputs from set A and maps them to outputs in set B, and f takes inputs from B and maps them to C, we can define what's called the composition of f and g to be this new function h, which is given by this thing over here, which might look like it's got way too many parentheses, but it's actually quite helpful. Remember, f is probably a function of x, but what we're doing over here is we're replacing every time that we see an x in our definition of f with whatever our function g of t is. So that's exactly what we did in this example here. We looked at our y, which we're thinking of as our f here, and we said, okay, well, wherever we see an x, we're going to replace it with the function g. And that changes over our function y from being a function of x to being a function of whatever g is. So in this case, g was a function of t. There are two different notations that get used kind of often interchangeably when we're talking about this. So the one is the notation f composed of g, like so. And this is quite useful because it tells you explicitly what to do. It says, take the formula for f, and wherever you see a variable in that f, replace it whole scale with whatever your formula is for your g. And that will change over your variables from whatever f was a function of to whatever g is a function of. The other notation that we sometimes use is this here. So this is just kind of like a little empty circle thingy. And this again is also f composed of g. And this says substitute g wherever you see whatever f's variable was. Okay, so back to the slightly more practical question of why would we ever want to do this. Well, in 1897, there was a guy called Amos Dolbear, and he noticed that crickets, a particular kind of cricket, I think it was tree cricket, snowy tree cricket, but I'm not entirely sure. Anyway, this particular kind of cricket chirped more when it was hotter. And in fact, there was a linear relationship between the two. And in fact, then he looked the other way around and he worked out that you could tell the temperature based on how many times per minute these particular crickets were chirping. And because he was working in the US, I believe, he was working in Fahrenheit. So he came up with this formula over here. So this says that the temperature in Fahrenheit is 40 plus a quarter times however many times your cricket is chirping per minute. But now we are actually not working in Fahrenheit. That's not very helpful. I don't really have a sense of what that means. So we might ask the question, what would this relationship look like if we wanted to know the Celsius temperature based on the number of crickets? Well, can we find this? Yes, we can. I'm going to add in another page here so we can do a little bit of working. The thing that we need to know is how do you convert Fahrenheit to Celsius and Celsius to Fahrenheit. And to go from Fahrenheit to Celsius, you use this equation over here. So let's think about if we can somehow use function composition over here. Let's look at Dolbear's original equation. Now it takes in as its domain the number of cricket chirps, and its range is Fahrenheit. So those are both numbers, but the point is it's taking in cricket chirps and it's spitting out Fahrenheit as a function. What about this equation over here? Well, this is a function which takes in Fahrenheit and it spits out as its output Celsius. So this seems like a really good candidate for function composition, because now if we compose our function, which way do we want to go? We want to say, okay, I'm going to take my cricket number of chirps and I'm going to get out some Fahrenheit, and then if I put that Fahrenheit into my Celsius Fahrenheit conversion, what I'll end up getting out is the Celsius given the number of cricket chirps that I input. So we're thinking of this function as our g and this function as our f. So let's see what happens if we do that. So we're going to say our function c composed with our function f, that's not helpful, not x, we need n, which is the same as saying c, and wherever you see an f, you put in the function for n, for f, will give us 5/9. Now I should have an f here, but I want to convert my f into cricket chirps, so I'm going to replace that f with this whole thing here, 40 plus 0.25n, and then I need to finish off the rest of my c equation, so that's minus 32. We can simplify this a little bit, so we've got 5/n and then 40 minus 32, so that's 8 plus 0.25n. And notice what we've now got is a new function, which I'm going to call c of n, and this tells us if I know how many cricket chirps I get per minute, then I can tell what the temperature is in Celsius. So this is the kind of thing that you might really want to use a function composition for. Okay, so just a little bit of terminology. You will sometimes hear the function g of x, which is kind of inside f of x, as referred to as the inner function. and analogously f is referred to as the outer function. And the thing to always remember is that the inner function gets applied first. So we're always thinking that we're looking at the inputs of g as the very kind of first step. Those inputs get put into g, which spits them out as its outputs, and those outputs of g get used as the inputs for f. So this also obviously means that the output set of g, so the range of g, sometimes called the codomain, I think here somewhere it says codomain, this is also, so the range of g needs to match the input set, so the domain of f. You don't have to have them all matching, but you need to have at least enough that you can make a function that goes through well enough. And this idea can also help you figure out the domain and range of your composite function. Obviously, your domain is going to be the same as the domain of g, your input, your initial inner function, and your range is going to be the same as the range of your outer function. So the second thing that gets applied, in this case, your f. All right, enough words. Let's actually do some practice. So I've got two functions here. I've got f of x is equal to sine of x plus 1, and g of x is equal to 1 over x. So you'll notice that, and this is a fairly common thing, I'm using the same variables for both. I'm using x for both the independent variable from f and also for g. But don't let that freak you out. We're going to work through this. Okay, so the first thing we want to find is we'd like to find f composed of f of x. So let's have a look at that. f of x. So what does this say? Well, this says I'm going to look at the function f of x, so that's this one over here, and whenever I see an x in there, I'm going to replace it with f of x. So I'm going to do this first one in quite a lot of detail, and we can speed up as we go along. Okay, so I'm going to say I'm going to look at my function f of x, and I'm going to write it down, and wherever I see an x, I replace it with an f of x. So I find when I started learning, this was the way that I did it. And then the next step is to say, okay, well, I don't really want to have a function that has another function within it. So wherever I see that f of x, I'm going to replace it with the actual formula for f of x. So I'm going to have sine of, okay, f of x is sine of x plus 1. And then I mustn't forget this plus 1 over there. Okay, so my composite function f composed with f of x is sine of x plus 1 plus 1. Okay, which is kind of weird, but there we go. Okay, so that might have come as a bit of a surprise. We can use the inputs of a function as inputs for itself again, provided that it has the right sort of range that we want. But let's do something a little more standard. So now I'm composing f with g of x. So this is, I'm using g of x as my input for f instead of x. So let's write this out again. So I'm saying I've got f of x, but wherever I see an x, I'm going to replace that with a g of x. Okay, let's now substitute in for g of x. My g of x is 1 over x, so I've got 1 over x plus 1. Okay, pretty straightforward. Now let's work out the opposite. Let's find g composed with f of x. So this says take g, and wherever you see x in its formula, replace that with f of x. Okay, so I've got g composed of f of x. So here's my g of x. I've got a 1 over x, but I'm going to replace that x with f of x. And if I now substitute in for the formula for f of x, I get 1 over sine of x plus 1. So the key thing to notice here is it really matters which order you do your composition in, because you'll see that 1 over sine of x plus 1 is definitely not the same as sine of 1 over x plus 1. So this bit tells you that the order of composition matters. So it's important when you're figuring out a composition that you know which is the inner and which is the outer. So remember, inner always goes first and then second. Just for fun, for homework, now you can work out F composed of G composed of F. Just take it slowly. We've already worked out part of it, but see if you can figure out. I'll put the answers in the final version of this. Now let's think about going in the opposite direction. So we've been creating composite functions, but we can also go the other direction and think about functions which we can find, which when put together give us a composite function. What am I talking about here? Well, here's a challenge for you. For each of these functions, a and b, that we've got here, so h of x and w of x, find two simpler functions, f and g, so that when we write the composite function f composed with g, we get h of x, and then do the same process and see if you can find out two simpler functions which, when you compose them, give you w of x. So maybe take a moment and do that, and then come back. Okay, so I'm going to have a look at h of x. And I want to find an f of x and a g of x, so that when I take f composed with g, I end up with h of x. Well, there are actually lots of answers here. So one possible thing, I look at this and I say, well, I could make my g of x this x squared plus 7. And I could let my f of x be x cubed. Let's just check if that works. I've got f composed of g of x. So this says write down my f of x, but wherever I see an x, I replace it with g of x. So here I've got x cubed, so I'm going to have g of x all cubed. And now substituting in for my g of x, I've got x squared plus 7 all to the 3, which is what I wanted. Okay, maybe you found something different. There are lots of different solutions. There is a good simple solution that always works. So we could also have said, well, I'm going to be really lazy and I'm going to let f of x equal x, and I'm going to let g of x be which I kind of feel like is cheating, but it still kind of works, because if you have a look at this, wherever I see an x in here, I'm going to replace it with x squared plus 7 to the 3, and so my f composed of g of x is going to be exactly what I wanted. There are other things that you could try. So one thing to do is to see how many you can find, how many different correct pairs of functions you can find that when composed give you this. And for homework, see what you can do with that one. And I'll put some answers into the final solution. Okay, so both of these techniques, both of these things that we've looked at with function composition, so being able to compose two functions, but also being able to take a more complicated function and break it up into simpler ones, are techniques that's going to come up quite a lot in various areas of the maths that we're going to do for this course. So please make sure that you are technically comfortable with this. I know it's not the most super interesting thing, but we're going to need both these techniques. So yeah, practice those. So a vaguely related technique is that of finding inverse functions. You'll see in a moment how they're connected. So earlier we were talking about crickets and the temperature, and we found that you could work out the temperature if you knew how many times a minute a cricket was chirping. But maybe you would like to go the other direction. So it might be useful to know if you know the temperature, how many times a minute you expect your cricket to chirp. I don't know, could be something you wanted to find out. So here we go. Can you take our equation, which we found earlier, this one, and convert it into an equation which tells you the number of cricket chirps given the temperature? Well, I'm pretty sure you can do that. You know that you just solve for n in terms of c, because we've got c in terms of n, we want to go the other direction. So let's just do that quickly. I've got c is equal to, let's see, 40 over 9 plus 5 over 36n. So I've just multiplied this bracket, this 5/9 in, and I've converted this 0.25 to 1 over 4, because I find it easier to work with fractions. Okay, now I'm going to solve for n. So I'm going to take my 40 over 9 over to the one side. C minus 40 over 9 is equal to 5 over 36n. And finally, I'm going to swap sides and multiply through by 36 over 5 to get rid of that. So I've got n is equal to 36 over 5 c minus 40 over 9. Okay, so this is now an equation which, as an input, takes a temperature and spits out the number of cricket chirps per minute. Whereas originally we had an equation that took in the number of cricket chirps and spat out the temperature. And what we've just found is what's called an inverse function. It is a function that goes in the opposite direction, so it inverts what you just did. Okay, let's have a look at the graphs of these two functions that we just found, because we can actually figure out quite a lot about inverse functions in general by just studying these two. And for that, we're going to head over to GeoGebra. So over here, I've plotted our first function. So this was the function which said our temperature in degrees Celsius is some function of the number of cricket chirps. So if we think about this function, our input is going to be the number of chirps per minute, and the output that we get is the temperature in degrees Celsius. Now let's look at the second function. So that I've plotted in green here. So our function g is the one that we found that said we will get the number of cricket chirps if we input the temperature. So if we were thinking about labeling the axes for this green graph, what we would do is we'd have our temperature in degrees Celsius would be on the x-axis, so-called x-axis, and what we'd get out would be, our number of cricket chirps. So this is our number of chirps. Oops, this is not working very well. Okay, so one of the things to notice is this looks very symmetric around the line y equals x. And there's a reason for that. So I'm just going to plot the line y equals x. And you can see that these graphs are mirror images around that line y equals x. So let's just make a note that this is the line y is equal to x. So what's actually going on here? There's obviously some fundamental thing happening here. Well, let's have a look and see what happens if, for example, I'm going to take 10 chirps and I'm going to figure out what the temperature is resulting from 10 chirps. So here what I'm doing is I'm really looking at my C of n. I'm saying C of 10 is equal to 6. Okay, good so far. But now what happens if I take this 6 as my input for my g function? So I'm going to say a temperature of 6. What number of chirps is that going to give me? Well, if I take a temperature of 6 and I follow that up there, it's going to give me 10 chirps. So if I say the number of chirps given to me by a temperature of 6 is 10. So far, this probably doesn't seem particularly interesting. But the thing to notice is that what I've really done here is I've said n of C of 6, sorry, C of 10, whoops, n of C of 10, because I started out with C of 10, is equal to 10. And in fact, and we'll have a look at this in a moment, one of the key things about inverse functions is they undo what the original function did. So see what happened here. Our function c took 10 and gave us out of 6. And then we plugged that 6 into n, and it undid that, and it gave us the 10 back. And in fact, it would work the other way around, around as well. So if, for example, we had started out with our n function, and we put in a 6, we would have given out a 10. And then if we put a 10 into our c function, it spits out the original 6. So the key thing that's happening here is an inverse function is a function which, in composition with the original function, undoes what the original function did. So let's summarize that. So I'll pull that image in here for the final notes. But in general, if we have a function that maps from a to b, and we have another function which undoes what that original function f does. So we've got our function f mapping from a to b, and we've got some other function g that goes in the opposite direction that undoes. So if we put f of a into g, then we get a back. And if we put b into g and then take f, and we get b back. And if that happens for every a in our domain and b in our range, then we say that f has an inverse function, and the function g is called the inverse of f. But of course, g is the inverse of f, but f is also the inverse of g. But the notation that we use here specifically, if we're taking f as our kind of first function and then we're finding the inverse, then we will often write this as f to the minus 1. Now this is horrible notation because it's very tempting to think that this must mean that this is 1 over f, but that is not the case. Okay, so when you see this over here, it means the inverse, not this thing over here, which is the reciprocal. So if you see an f to the minus 1, because we're talking about functions, it says find the inverse. It's not saying take 1 over. It's very annoying. Sorry, mathematicians, they like to think that they're completely rigorous with the notation, but they're just not. Okay, so can you always find an inverse? Unfortunately not. We can only find an inverse for a function if it's what's called a one-to-one function. What does this mean? It means that each input for our function gets mapped to a distinct output. In other words, if you look at the output set, for every output you know exactly which input it came from. There couldn't be 2 inputs that it came from. So in pictures, because I find that helps a little bit, what you want to think about is things like, so in fact I want to go back to our very first picture that I drew here. See, I told you they'd be useful. And we're going to go down all the way back. Let's get rid of this. Haha, okay, so that was probably too long, but anyway, here we go. What am I talking about? So notice in this first function that we've got over here, if I have a look at anything in the range, I know exactly which output it came from. So if I look at 5, I know that 5 came from 2. So I could create a function that went from 5 to 2. I know that 6 came from 1. And I know that 7 came from 3. So I can create an inverse function for this guy over here. So if we call this our function f, then this is f inverse. But if I try to do the same thing with this function over here, which I'm going to call g, so let's try. So here I would have a smiley face and 1, 2, 3, but I want to create a function, which means my smiley face can only go to one element of 1, 2, 3. But the problem is over here, I don't know which one it should go to, because smiley face came from 1, but it also came from 2, and it also came from 3. So I have no idea how I would create a function. Because remember, a function says smiley face has to go to one and only one of the elements in my output set. So our green function over here, our f, is 1 to 1, and our red function over here is not 1 to 1. And you can't find an inverse. All right. So how can you check? Because it might be a bit of a pain to be actually drawing set diagrams. Well, the useful thing is you can actually use what's called the horizontal line test. Not to be confused with vertical line test, which you might have learned about finding if something's a function. Okay, let's see what I mean. So here I have a function. And I'm going to draw another function over here. And the thing that we want to do is test which one of these is 1 to 1. And the horizontal line test says, well, if you draw a horizontal line, and you kind of imagine moving that line down, all the way down your function, if the horizontal line only ever cuts the function once, then it's 1 to 1. On the other hand, if you imagine you've got some horizontal lines with this function which cut multiple times, and therefore it's not 1 to 1. Does this make sense? Well, in terms of our definition, yes it does. Think about what this is really saying. If I'm looking at this function over here, at any point I can pick any value on my y-axis and I can draw a horizontal line, and it only cuts my function in one place. So there's only one possible x value that it can come from. And that's exactly what we're looking for when we're looking for a one-to-one function. We want a function where, given an output, we can find a unique input. But if I try the same thing with my function over here, if, for example, I pick this y value, I look at this horizontal value, this horizontal line over here, well, there are 3 different values of x that give me the same output. So if I was trying to invert this and I was trying to guess which input gave me this particular output, I couldn't, because it might be this one, or it might be this one, or it might be this one. So I wouldn't be able to find a unique output for my new inverse function. So that's the horizontal line test. So that's kind of 2 ways of looking, and you can imagine if you wanted to see if a table form of a function was 1-to-1, you'd basically just need to look down your outputs and see if you had duplicates in your outputs, because that would mean that there were two different inputs that got mapped to the same output, and then you wouldn't be able to find an inverse. Alrighty, so here's something for you to check. So I'm going to leave these for you to do, and I'll put the answers in the final solution. So we're going to take this function x cubed plus 1. Now the first thing that I would urge you to do is check that this is 1-to-1. So this is part 0. Okay, that's shorthand if it's 1-to-1. You can sketch it. You can always just sketch it in Wolfram Alpha or GeoGebra or something. Just check that it's 1-to-1. Use the horizontal line test. And then find the inverse, and then find the inverse composed of the original function, and vice versa. See what you find, and see if you can explain your findings. All right. See you for part 2.